So this is a brief lecture on the material in section 6.3. And so what we're going to do is we're going to try to calculate volumes of revolution and also volumes from what they call slicing or known cross section. So I think this material is hard. I think 6.2, 6.3, 6.4 is difficult. And you have to really visualize, you have to have a good understanding of the geometry of the problem. And if you don't, it can be really hard just to, find the limits of integration and to really understand, what it is that you're calculating. So, and I think 6.3 and 6.4 can, be harder than 6.2 because now we're dealing with three-dimensional area. And I know I have a hard time drawing three-dimensional object, especially when it comes to maybe some of these unusual shapes you see in the graphs. But I think, so let's say we have this, let's just look at that yellow, this drawing right here. And so this first thing is going to be like what we call the disk method. And we're going to be using the formula for the area of a circle, pi r squared. Okay, so if you look at that, so look at that function y equals f of x, and then we have that shaded in region that's in yellow. And suppose we took the height, just go out any point x, and so we go up to f of x or y, and then we just rotate around the x-axis. So we're going to be generating a solid, like a three-dimensional object that way. I think you can maybe tell from the drawing that that's three-dimensional. And if you just kind of take one cross section of this, so you're basically rotating the curve around the x-axis. You're rotating the whole thing around, and the heights represent the radius of a circle. And so what you see in the drawings, it's like the cross section of one of the discs or the cross section, the cross section of one of the circles. And in this case, the radius is f of x. And then we know, so for that red cross section that's shaded in there, we know that, for some fixed x, we know that the area of the circle is pi f of x squared. So and in this case, the curve starts at x equal to a and ends at x equal to b. So the area of the volume, if we're going around the x-axis, is pi, let me make this a little bit bigger, is pi going from a to b of f of x squared dx. So that's going to be the basic formula for this. And I think the hard part will just be computing f of x, or what is the radius? If there is a hard part, that's the hard part. Because sometimes we're not going around the x-axis, sometimes we're going around the y, sometimes we're going around like y equals a, where a is not equal to 0. Like let's rotate around the line y equal -2 or y equals 3 or something like that. So, but I think once we do a few of these problems, then it's not too bad. Okay, so let's just look at this really great example right here. Oh, problem 1. So we have the curve. So this is a great example. You have this curve here, y equals x plus 1. So you have to, so the thing is, we want to get an idea of what the boundary of this looks like. And what we're doing is, okay, so here's like y equals x plus 1. Here's the line y equals 0. It's the x-axis, right? And we're going from x equals 0 to x equals 2. And so there's your line y equals x plus 1. So you go at any x, you go all the way down to the x-axis. And that's the radius of your circle. And you're going to rotate that radius around the x-axis to kind of generate some kind of almost cone-looking object there. And so again, so we know that in this case, the function is x plus 1. So the volume, okay, so just remember should have written this down. Let's just remember, so this is the y-axis is x equals 0, and we're told in the problem it goes to x equals to 2. Okay, so the limits of it, so we're integrating, we're starting at x equal to 0, and we're wrapping the radius around we're rotating the radius around the unit circle, x equals 1, x equals 0.1, x equals 0.2. So we just continuously do it. And so turns out the volume turns out to be pi from 0 to 2 of y squared. In this case, y is x plus 1. And now in that integration we can do, you just have to, well, we could actually do a substitution. You might see that that's x plus 1 cubed over 3. But you can always make a substitution, or you can expand. Okay. So now here's another fun problem. Again, here's another one. So in that first one, yeah, we had lots of lines. Okay, the line y equals x plus 1. This boundary was formed by 4 lines, right? Y equals x plus 1, y equals 0, which is the x-axis, x equals 0, which is the y-axis, and x equals 2, which is parallel to the y-axis. But okay, so now for number 3, we don't have as much information. We're told region enclosed by the square root of minus x squared, which turns out that's actually the upper half of the circle of radius 4. Okay, but so there's our, but anyway, there's the region. It's a semicircle. You know, if we look at the region, the area between the square root of 16 minus x squared and the x-axis, here we get that semicircle, and we're going to rotate it, like in here in red, we're going to rotate this around. We're going to get actually a sphere in this case. Oh, it's right here, volume of the sphere. It turns out, yeah, so the and the radius, so you have to actually find the points of intersection. Where does this intersect the x-axis? You might just see this by observation. It's at 4, 0 and -4, 0. Okay, so you're going to integrate from -4 to 4. We can use symmetry and go from 0 to 4. And then, of course, we know that the height, we know that we can recognize that this is the a semicircle of radius 4. So up there, that's 0, 4. Okay, and so we're going to rotate this around and get a sphere where the radius is 4. So yeah, it turns out that the, and we could have done this actually without just using our knowledge of geometry, and the volume of a sphere is 4/3 pi r cubed, because that's a way of checking your answer in this particular problem, to make sure you actually got the volume of the sphere is radius 4. Okay, now on to the famous washer method. So this is one of my favorite methods in calculus. And luckily for me, we're teaching in Calc 1 and not Calc 2. Because it used to be in Calc 2. Now it's in Calc 1. So, okay, so basically it's a solid revolution, but there's a hole in it. So I guess it's kind of like a washer, like in your building stuff, or like a donut, right? The donut, it's this solid, but it's got a hole in it. Okay, so let's say we want to find, let's say we take this yellow region right here. So we have this curve, y equals f of x, and that's the one that's higher up, and y equals g of x is below it. And we're going to rotate around. Let me see here if I can do this blue here. Yeah, so like we're going to just, here's like a blue line here, and we're going to rotate that around the x-axis. But you see there's going to be like a hole in the middle, right? Because the top starts right up here at the top of f of x and stops here where we get to g of x. And we're going to rotate that around. But so how would we get that volume? Well, just pretend, first let's take the volume. Let's just take the volume of, okay, let's say we're going to wrap around y equals f of x around the x-axis. And then subtract off the part when we wrap around g of x around the x, that volume. And that's where you get the washer method. Okay, so you're finding the entire volume for wrapping y or rotating y equals f of x around the x-axis, but then you're taking out that middle, the volume that we get from rotating g of x around the x-axis. So, and yeah, so then if the radius of the outer curve is r naught, and the radius of the inner curve is r sub I, yeah, you get this integral here. But basically, I would have written it, or I guess I would write it like this, just f squared of x pi f squared of x minus g squared of x. And then just multiply it by, we're not given enough information in that drawing there to know what the limits of integration are. Okay, so now here's kind of a fun problem. Okay, so we're going to wrap around, I keep saying, maybe I should be saying rotating. Okay, so the region bounded by x squared plus 2, so that's a parabola. It's one of our favorite parabolas. It's the vertex is at 0, 2, and then the line with the negative slope minus x plus 4. And we're going to revolve it around the x-axis. So the first thing so you must graph this to be able to do the problem. And then to find the points of intersection, you have to solve for them, right? We want to know where x squared plus 4 is equal to x squared plus 2 equals minus x plus 4. And you just solve the quadratic, we get this quadratic equation and you solve it, we get x is -2 and x is 1, right? So, this would be, there x would be -2, and then the other one, x equals 1. So those are our limits of integration. And basically what we're going to do is, okay, well, let's find the volume when the height, the radius is equal to x squared plus 2. We're going to rotate that around the x-axis, and then we're going to rotate, and then we're going to find the volume for when the height is minus x plus 4. And actually, minus x plus 4, the important thing is which curve is above. And it's actually graphing really, I can't look at this necessarily until, sometimes I can, sometimes I can't. Maybe if I just substitute a few points in, but graphing will just tell you immediately. So graph this on your graphing calculator. Sometimes I go to Wolfram Alpha to do the graphing because I like their graphs. But maybe you don't have, I don't know, maybe on your phone it doesn't look great. I need to do that on a computer. Anyway, or use your graphing calculator that we asked you to buy out of your hard-earned money. So you can use that too. But anyway, let's see here. Okay, so to find this region, so first find the volume by rotating y equals minus x plus 4 around the x-axis, and then rotate x squared plus 2 around the x-axis and subtract that off, and you get here. So here's your basically, so it's x, so the radius of the outer one is minus x plus 4 squared. The radius, like of the inner of the lower curve is x squared plus 2. So you have to square that. So it's, remember, it's pi f squared of x minus g squared of x. That's your integrand. And you might, graphing it and just doing the algebra, and especially graphing, will really tell you where the limits of integration are. And so we could actually, now that we know the integrand, we can do that one. We don't necessarily need to. I assume you know how to. We all know how to do that. Okay. But the hard part is for these is setting up the problem. Oh, here's a fun problem. Problem number 4. Okay, so the region bounded by x squared plus 2 and minus x plus 4. Oh, is that the same curve? Is that the same parabola? Oh, I'm glad that it is. I'm glad it's the same parabola because, yeah, I like x squared plus 2 definitely is one of our favorite parabolas. Anyway, that's the lower curve. Minus x plus 4 is the higher curve. But now we're wrapping around. I keep saying wrapping, I should say. We're rotating around the line y equals -2, which is parallel to the x-axis, right? X-axis is y equals 0. So what is the radius of the higher curve? Now the higher curve is y equals minus x plus 4. So minus x plus 4 tells you the distance of any point from the x-axis, but we have to go 2 below. Okay, so it's actually minus x plus 4 or plus 2 or minus -2. Right, so that's the radius of the higher curve, and the lower curve, the curve that's underneath, it's x squared plus 2, and then you just right, the distance on the parabola from the x-axis is x squared plus 2, but we're rotating around once again around the line y equal -2, so you have to actually add 2 to it. So the radius of the higher curve is minus x plus 6. And the radius of the inner curve is x squared plus 4. And it's only because we're rotating around y equal -2. If it was y equal to 0, we would just use these original, it would be the original functions, minus x plus 4 or x squared plus 1. So basically you have to subtract off, whatever y equals, you subtract that off. In this case, we're subtracting off -2, so we get plus 2. Okay, here, so well, let's see. This is kind of the same thing, I guess. Only now the line is above the curves. Okay, so in this case, the higher curve is actually closer to the line y equals 6 than than x squared plus 4. Okay, so what would be the what in this case, what's the radius here? So because we're rotating, if you can see this, here's y equals 6, and this is y equals, and then here is your radius. What's the distance between those two? So it's 6 minus x minus -x plus 4, right? So the inner radius here is 6 minus x plus 4. Okay, and so what do we get there? We get 2 plus x. And okay, so in this case, that the curve that's visually above minus x plus 4, that's the one that's closer to the line y equals 6. So that's gonna, so when we rotate that around, when we rotate minus x plus 4 around the line y equals 6, that's gonna generate the inner volume that we're gonna remove. So that's why we subtract that off. And then the distance of x squared plus 2 from the line y equals 6. So well, we know what it, so we know it's 6 minus, yeah. So if we go like here, this red point right here, we go all the way down to here, that would be 6, right? And we know that this height here is x squared plus 2. Let me do that again. Here we know that this height here is x squared plus 2. So this outer, the higher radius, or the bigger radius, is x squared plus is 6. It's right here. It's 6 minus x squared plus 2. Okay, and so and which turns out to be 4 minus x squared. Okay, so the volume is pi. Okay, it's always pi. Radius of the outer squared minus radius of the inner squared. So the outer is the one that's farther away from the line. So in this case, x squared plus 4 is farther away from the line than x plus 2. Okay, so we've done a bunch of those. Students, also I have to tell you something. We're jumping the gun. I mean, I'm not, sorry again, a friend gave me these notes. We're jumping the gun a little bit, I guess. It's kind of a strange expression. We're getting ahead of ourselves. That probably is a nicer thing to say. This f of x equal, that's in chapter 7. I think it's the last thing we learned. Okay, so so we'll just skip this one. You might well skip it too, unless you're familiar with it, or maybe you'll go back. I don't know. Now we can also rotate around the y-axis. So, so in this case, we have this sideways parabola, x equals minus y squared plus 4. And again, if you're having a hard time visualizing those, just change the role of x and y and graph on the regular x-axis. So remember, the problem is we have to go back to y when we do this. Okay, so we want to rotate minus y, x equals minus y squared plus 4 around the y-axis. So again, you're gonna have to find the points of intersection. When is x equal to 0? Right, because this is the line x equals 0. So you want to know, first of all, what is where does it intercept the y-axis? So so you'd have to solve minus y squared plus 4 equals 0. Is that right? And so you get y equals 0 and y equals 4. Yeah, so you know your limits of integration are from 0 to 4. And then this distance from the y-axis, you take any point here and you're going sideways. And we're told that distance is, well, that's x, right? This is x. And in this case, x is equal to minus y squared plus 4. So in this case, when we're rotating around the y-axis, we get pi 0 to 4 minus y squared plus 4y. And again, the important thing to get the limits of integration, yeah, you have to actually solve minus y squared plus 4y equals 0.